Example 4.4.9. This one says, you are saving for retirement. You just turned 22 and plan to make your first deposit of $4,400 to your retirement savings account at the end of this year on your 23rd birthday. Looking at your expected income and expenses, you believe that you can save $4,400 at the end of this year, and then will continue making annual deposits until your last deposit on your 64th birthday. You expect that your income will increase 3% per year on average over your career, and you plan to let your savings grow at the same rate. That is, you will make each deposit into your retirement savings account 3% larger than the previous years. How much will be in your retirement savings account immediately after making your last deposit on your 64th birthday if you expect to earn 7% per year on your retirement savings? Okay, so this one is really the other half of the previous example, 4.4.9, where we were looking at how much must be saved in our retirement savings account in order to fund a particular withdrawal scheme in retirement, in order to fund our retirement income. This is backing the timeline up even further, and it's looking at how do we save to make sure we have that particular amount in our account. All right, so we've got a time value of money problem, so we're going to use our three-step process where we're going to start by mapping out the cash flows on a timeline so that we can then use that timeline to identify the type of cash flow that we're dealing with, which is step 2. And then once we know the type of cash flow we're dealing with, in step 3, we can then select the appropriate tool that we can use to evaluate that cash flow with. So let's start by mapping this guy out. All right, with this one, today, right now, is our 22nd birthday. So I'm going to keep track of 0 through however many actual cash flows we've got here and our age on 2 separate lines to make sure I get the timing of the cash flows exactly right. Today's our 22nd birthday. We've just turned 22. We're not going to do anything today. We are planning to make our first deposit of $4,400 into our retirement savings account at the end of this year. So 1 year from today, on our 23rd birthday, we're going to make that first deposit of $4,400. So we've got an entire year to save up that amount and drop it into our retirement savings account. After that, we're going to continue making annual deposits. So 2 years from today, on our 24th birthday, we're going to again make another deposit, but it's going to be 3% larger than the last one. So the $4,400 deposit that we made, we're going to multiply that times 1.03 to grow it by 3%. Right, and that's going to equal 4,400 times 1.03. So our second deposit is going to be $4,532. Right, and that pattern is going to continue. Let's just draw a few of these out. 3 years from today, on our 25th birthday, we want our deposit to grow again by 3%. So it's going to grow by 3% over the first year and then by another 3% over that following year. So that original $4,400 deposit is going to grow by 3%, 1.03, twice at this point, 3 years from today. So that third deposit is going to be $4,667.96. Right, and that pattern is going to continue. So I'll use our ellipses here, ... to say this pattern continues out to our 64th birthday. So we want to know how many total deposits we're going to make over this period. Well, time period 0 was our 22nd birthday. So if we take the last one, age 64, minus the age at time period 0, or today, so 64 minus 22, we're going to make a total of 42 deposits into this account, or 64 minus 22. a little bit neater. So that 42 total deposits we got by taking age 64, which is the end of our timeline, minus the age we are starting at, that is the age over the 0 tick mark of 22, so 42 total deposits. And so our very last deposit of $4,400, if we want to figure out what amount it is, which we don't actually need to know, we'll see in a minute when we use the formula, but just so we can get a feel for the size of the cash flows we're talking about here, we need to take that 4,400 and grow it by 3%, in this case 41 times. And here's why 41. I know we've got 42 total payments, but the very first payment doesn't grow. It starts at 4,400. We don't grow it for the first time until the second payment. So if we look at the exponents on these growth factors, for the first ones that we mapped out, I'm going to put this 1.03 raised to the 1 here. We don't typically write that, but just so we can see the exponent. Anything raised to the 1 is just itself. Under the second tick mark here, I've got my exponent raised to the 1. Under the third tick mark, our growth factor is 2. It's raised to the 2. So our exponent on the growth factor in this particular setup is 1 less than the tick mark that it appears under. So we can follow that pattern to figure out what the last cash flow is. So let's figure out what that is real quick. 4,400 times 1.03 raised to the 41. That last deposit is going to be $14,783 and roughly 56 cents. All right, we've got one more piece of information we have not accounted for yet. That is our interest rate. We think we're going to be earning 7% on our savings, so we'll get that guy on there. And now we have all of the information given to us in the problem collected on our timeline. So now it's time to go to step 2 and figure out what type of cash flow we're dealing with. Now, we have cash flows at regular intervals that are growing at a set rate. There are only 2 types of cash flows that we have that grow at set rates. It's either going to be a growing perpetuity or it's going to be a growing annuity. And the difference between those two is whether or not the cash flows stop at some point. A perpetuity goes on forever. It never stops. And in this particular case, the cash flows do stop. On our 64th birthday, we're going to make that final deposit, we're going to retire, and then we're going to start drawing down our retirement savings. Okay, so pretty sure this guy is going to be a growing annuity. Let's take a peek at our cheat sheet just to be sure. I'm already scrolled down to the growing annuities, which is the third option under the annuities section. And this guy is defined as a finite stream of cash flows growing at a fixed rate and paid at regular intervals, where finite just means that it stops. It doesn't go on into infinity. And the timeline example that we have here is calculating present value, but we could find present value, future value, whatever. Inside of this, it's really the structure of the cash flows that we're interested in. We have a cash flow at the 1 tick mark, a cash flow that's 3% larger at the 2 tick mark, and that pattern continues on out to the last cash flow, which is still growing at 3%, and then those cash flows stop. So sure enough, this does fit both the written description and the timeline example of a growing annuity, so that is what I believe I'm dealing with here. Okay, so we have a growing annuity. And we have a growing annuity. There's a little bit of an internal groan that I let out because the time value money keys in the financial calculator are just taken off the table. The only solution tools available to us are the growing annuity formulas and the spreadsheet. And of course, we're not looking at the spreadsheet solutions in these videos, although they are in the text, because typically you're just not going to have access to that during an exam. So we want to focus on the ones that we need to practice over and over again. So for the growing annuity formulas, we have 2. We have the present value of a growing annuity and we have the future value of a growing annuity. So which one we use just depends on what information we are given and what we are looking for. So let's take another quick look at this problem and see if we can figure out which one of those 2 we are solving for. The question at the end of this example says, how much will be in your retirement savings account immediately after making the last deposit on your 64th birthday if you expect to earn 7% on your retirement savings? So we're looking for an amount at the end of this timeline. After we make all these deposits and earn all of our interest, what amount is going to be in our account at that time period. So that is future value. We're looking for a terminal amount here after all is said and done. Present value will be what's at the beginning of the timeline there, which is not what we're looking for in this case. We are looking for future value. Okay, so we are going to select the future value of a growing annuity formula. Which is this guy right here, and it is just as ugly as it looks. But we'll break it down piece by piece and see that it's not too bad to deal with. All right, so the future value of a growing annuity is equal to the payment. Actually, it's going to be that first payment times the quantity 1 plus r raised to the n minus 1 plus g raised to the n divided by r minus g. All right, so let's plug in all of the information we have from this one. This payment that we want to use is actually the first payment in the annuity, and it'll be that way in every case. It's $4,400. Times 1 plus r. R is our interest rate in this case, which is 7%. In this problem, we expect to earn 7%. 7% as a decimal is 0.07, and 1 plus 0.07 is 1.07. N can be a source of confusion here. N, as always, is going to be the total number of payments in the annuity. Okay? And so for this one, we've set our timeline up so that we can track the number of payments because the first payment falls under the number 1 tick mark. And so the last payment, it starts counting right there with 1. The last payment is under the 42 tick mark. And so we know there are 42 total payments in this. So N is going to be 42. The confusion can set in or be introduced if we accidentally look at the exponent on our growth factor. And as we talked about, it is undercounting the number of payments by 1 because the first payment isn't growing at all. The growth doesn't set in until the second payment. And so we don't want to use the exponent on our growth factor to count the number of payments. We want to actually look at the tick marks to make sure we get the correct number of payments. So for this one, that's 42 total payments. We're going to subtract from that 1 plus G, or 1 plus the growth rate in the cash flows. And in this example, the cash flows are growing at 3% per year. Each one is 3% larger. And 3% expressed as a decimal is 0.03. And 1 plus 0.03 is going to be 1.03. Again, raised to the n, which is 42 in this case. And we're going to divide that whole thing by our interest rate of 7%, or 0.07, minus the growth rate in cash flows, which is 3%, or 0.03, expressed as a decimal. Okay, let's work this one piece by piece. We could, as before, we could punch it in from left to right just like it's written. It'll work out okay as long as we type it in correctly. But I will often not type it in correctly and won't realize that I've done it, or I'll do it at the very end if I do realize it and I've got to start all the way over. So I find these problems a little faster to work if I'm having to use the calculator to solve them, just using arithmetic. If I break them down into chunks and then store values as I go and write down what the stored values are and where I've stored them. So that way, when I make a mistake, not if, but when, because it's going to happen, I can go back and track down where the mistake is without having to work the entire problem over and over and over again until I get the same answer multiple times in a row. So the 4,400 is straightforward enough. I don't have to calculate anything there. Let's start by calculating this numerator here. I'm going to raise 1.07 to the 42, and if I'm using the BA2+, the way that I do that is by typing in 1.07, and I press the Y to the X key to raise the value on the display to the number that I type in next. In this case, I want to raise it to the 42, so now I'll type in 42, and I'm going to press equals to go ahead and force it to do to do that function. So it took 1.07 and multiplied it by itself 42 times. So that's 17.1443. All right, and we're going to subtract from that 1.03 raised to the 42. So while this number is on the display, remember it's worked out to 13 decimal places, I'm not going to clear it out. I'm going to leave it on the display and type in the rest of this function or the rest of this expression so that it uses the full 13 decimal version of it. We could also store it right here just in case. There's not much to type in from here, so I'm not too worried about it, but it wouldn't be a bad habit to get into to go ahead and store this value if you wanted to. All right, so while this is on the display, the 17.1443, I'm going to say subtract then 1.03 raised to, or y to the x, 42, equals, and when I do that, it's going to do both the exponent. It raised 1.03 to the 42, and then subtracted that from the 17.1443. And so the total value there is 13.6836. So that's the total numerator value. And that's going to be divided by 0.07 minus 0.03. I can go ahead and handle that myself. That's 0.04. All right, so I'll take this value again while it's on the display, and I'll divide it by 0.04. Okay, and I will go ahead and store that value just in case. So we've got 4,400 times 342.0890, and I stored that guy on the 1 key just in case I accidentally mess something up from here. So while this number is on the display, again, I want to use the full 13 decimal version of this, not just the 4 decimal approximation. So while this number's on the display, I'm going to say times 4,400. I'm going to type in 4,400 and get a total value of $1,505,191 and roughly 70 cents. Okay, so we found a value. That's great. What does this mean? This means that if we make all 42 of these deposits in the amount that we plan to make them in and earn 7% interest on our savings, then when our 64th birthday arrives, we will have saved $1,505,191.70. Which, if we remember from the previous example, in order to fund that retirement savings of $80,000 a year that grows at 3%, and so on our 100th birthday, we're actually withdrawing $250,000 almost, $225,000, we needed to have $1.49 million saved. Well, if we can follow this savings plan by depositing $4,400 per year, and then letting that grow by 3% per year as our income grows, then we'll actually have more than that saved. We'll have $1.5 million saved, which will be more than enough to fund that retirement plan. Now, I know if you're like me, the idea of saving $4,400 over the course of a year sounds like a lot. When you graduate, particularly if you're in finance or accounting or one of the disciplines that tends to have a higher starting salary, you're talking about saving about 10% of your overall income, which is the general advice. You generally want to save about 10%, just both for retirement, rainy days, and so on. So this is not an onerous requirement, and if you're 22 when you're exiting college and starting to work, you easily have 42 years to save for retirement. In fact, you're probably not going to retire at 64. Our life expectancy keeps getting longer and longer, so our working age keeps getting longer and longer. You'll probably have even longer to save for retirement. So as long as you start early enough, you can easily accumulate over $1 million in your retirement savings account and then draw on that in retirement.